Good afternoon and welcome back to the AP Physics 1 review sessions. My name is Joshua Beck. I'm coming to you from Clayton High School. Hope you guys have been enjoying the lessons from Greg the past couple days. We've got another lesson planned for you today. We're going to talk about conservation of linear momentum, but hopefully in a manner that's maybe a little bit different than what you've done typically. So our lesson overview today is going to be a little bit different. Instead of starting with yesterday's practice problem, I'm actually going to save that for a little bit later in the class. So hang on to that. We'll definitely be coming back to that. But I want to cover a few things leading up to it. So we're going to start by reviewing impulse and momentum for single objects very quickly, and then we will dive into conservation of momentum within a closed system where we have multiple objects. Then we'll talk about kind of an alternative approach, or maybe even two different alternative approaches, ways to view a collision from a conceptual standpoint that can help you navigate your way through, even if you don't have all the numbers that you would prefer to have. Then we'll finally go over yesterday's review problem, and then I'll leave you with some practice for tomorrow. Okay. So I want to dive right into it with a quick example here, just discussing momentum of individual objects. We'll start out, we've got a school bus. We'll say it drives by your house at a speed of, say, 13 meters per second. I'm not going to do any big calculations here, just a quick analysis. Then a motorcycle drives by and it has a speed of 20 meters per second. So I want you to look at these two statements coming up. Student A says, hey, both objects are moving, but the school bus has a much larger mass, so it must have more momentum. Okay. I hear you. Student B says, well, both objects have mass, but the motorcycle is moving faster, so it must have more momentum. Interesting. So student A is assessing the mass of these two objects, and student B is assessing the velocity or the speed of these two objects. So what would you say? Well, you might think, if I'm going to answer this question, I need to know more information. I need to know the mass of these things. Well, you're on the right track here. Momentum is going to be calculated with a very simple equation. It's calculated with m times v. Okay. Now, in this particular case, the speed of the motorcycle is roughly 1.5 times the speed of the bus. So that means that in order for the bus and the motorcycle to have equal momentum, the mass of the bus would have to be 1.5 times the mass of the motorcycle. So that when we take m times v, we'd end up with the same product. Now, does that seem reasonable? Does that seem likely that the bus has a mass of 1.5 times the motorcycle? Well, I think in this particular case, we can safely assume that the mass of the bus is not only greater than 1.5, but let's say way, way, way greater than 1.5 times the mass of that motorcycle. So in this particular case, it's most likely that the bus has more momentum. Now, I checked, I didn't know off the top of my head, but I checked to see, hey, what's the mass of a bus? What's the mass of a motorcycle? The mass of a bus is actually roughly 75 times larger than that of the motorcycle. Okay, so in this particular case, the bus definitely has more momentum. Now, could the motorcycle move in a way that it does have equal momentum? Well, if momentum is calculated with m times v, well, the motorcycle has a much, much smaller mass, right? 75 times smaller. So in order to have the same momentum, it would just have to have a velocity that's 75 times bigger. Okay, so is that possible? Well, let's see. The school bus was going 13 meters per second. What's 75 times that? Let's see. 975 meters per second. So is it possible for the motorcycle to move in a way so that it has equal momentum as the bus? Well, mathematically, sure. But this is a physics class, so we can put some realistic parameters on here. 975 meters per second. Well, that sounds fast because it is, right? Think about the speed of sound, a little over 300 and something, 300 to 350 meters per second, depending on conditions, right? So this motorcycle would have to be going 3 times the speed of sound. So while mathematically there's a way for this motorcycle to have the same momentum, realistically, within the constraints of our physical world, is it possible? I'd say probably not. Okay, so when we're going to compare the momentum of two different objects, and this will be important once we start looking at our systems, is it enough to say that an object has more momentum simply because it's moving faster? Well, no. See, the motorcycle was moving faster, but it did not have more momentum. Now, is there one situation where it would be enough to just address the velocities? Yeah, if they both have the same mass. So if we're comparing two carts with equal masses, well then saying one is going faster than the other, that is sufficient. Is it enough to say that the momentum is larger just simply because an object has more mass? No. Now, if they're both going the same speed, then yes, the one with more mass would have more momentum. But what's the best way to always justify? What's the best way to justify which of two objects has more momentum? Well, you can use this phrase right here. The product of mv. The product of mv is what's important. Yes, mass plays a role. Yes, velocity plays a role. So if you want to figure out which object has more momentum or less momentum, don't just compare m and v, compare the product of m and v. Okay, that's a surefire way that you can make sure you're explaining things thoroughly. Now, the momentum of an object can change. We can change the velocity of an object a variety of different ways. So how do we change something's momentum? Well, we call that an impulse, and we apply a force for a certain period of time. Now, a few quick reminders about impulse. I don't want to get too far into this, but a few reminders. You can screenshot this slide once I finish these three reminders if you want to go back and look. These are all vectors, so the direction matters. If I apply an impulse in the direction it's moving, then it'll add to the momentum. If I apply an impulse in the opposite direction of its motion, then it will actually decrease the momentum. It might bring the momentum all the way to zero. It might even give it some momentum in the opposite direction, so the sign might actually switch. If the force changes during an impulse, you can't just use the initial force, the final force, or some random number. You have to use the average force. Typically, if you have a problem where the force is changing, they'll give you the average force, or they'll show you that force on a force versus time graph. We'll look at these in a few minutes, just briefly, so you'll see what they look like. But if you were to graph the force versus time, the area underneath that curve will equal the change in momentum during that time. Now, if you're looking at one of those graphs on an exam, just be careful of the units. A lot of times these collisions happen very, very quickly. So the time intervals are very, very small. So the graph might not be scaled with seconds. It might be 10 to the -2 or 10 to the -3. So just something to watch out for. So I want to transition away from individual objects and instead put them in a system, put them together. So which of the following would be true for a collision between two objects in a closed system? Closed system means that there's no external net force. Okay, so we're not going to have a frictional force that's slowing these things down as they move. We can have external forces. We might have the force of gravity and the normal force of attract, but those are balancing each other out. There's no net external force. So that keeps it a closed system. So first, let's talk about energy. Kinetic energy is blank within the system. This is during a collision. Give you a second to decide which one of these you think is the best answer here. If you said that kinetic energy is only sometimes conserved, you are correct. Now, why is it only sometimes conserved? Well, during this collision, there's going to be a certain amount of energy possessed within that system. Well, when the collision takes place, if these things collide and they make a whole bunch of sound, if they generate some heat, then those are two forms of energy, both thermal energy and sound energy. This is a type of, or these are types of energy that might leave that system. That energy doesn't disappear, it's just no longer possessed within that system as kinetic energy. So it might dissipate out into the room or into the world or into the outside environment, some of this thermal energy and some of this heat, okay? Now, can we create an elastic collision where kinetic energy is conserved? Well, technically, if they come in contact, then there's going to be some energy dissipated due to sound and heat, but we can get really, really close. So if the collision is very, very quick between two really, really solid objects, like think two pool balls or something like that, or if I can have two carts with magnets so they push against each other like this without the big crashing in between them. Okay. In a problem, you'll be told if it's elastic, that would be energy is conserved. Inelastic, meaning that the kinetic energy is not conserved within the system. That energy still exists in our world, it's just dissipated out of the system. Or you might have to calculate the energies and then decide if it's elastic. Okay, enough about energy. Our focus today is really on the momentum. So take a look at the second one. Is the momentum, or the momentum is blank within a system. This is going to be during a collision between two objects. Now, momentum is always going to be conserved here. As long as this is a closed system, then the momentum is going to be conserved. Okay, so the question is why? Well, the answer actually comes down to Newton's third law. The reason why momentum is conserved deals with Newton's third law. Now, before I address this in greater detail, I want to address a few misconceptions about Newton's third law. It's easily misunderstood, right? Most people know the expression, oh, equal and opposite forces. But if that's all you remember about Newton's third law, you're doing yourself a disservice. Because I could have a block hanging from a string in equilibrium. I've got the force of gravity down, I've got the tension pulling up. Those are two forces that are equal in magnitude and opposite in direction, but that's not an example of Newton's third law. See, with Newton's third law, we're not talking about two forces on one object. We're talking about two forces acting on two different objects. One object hits another object and applies a force to it. During that collision, this object applies an equal and opposite force back to this one. Okay, so it's two forces, one felt by this object, one felt by this object. Those two forces will be equal in magnitude and opposite in direction. Now, because it's two forces acting on two different objects, these two objects are free to accelerate or not, depending on their own situation. If one is like attached to the ground, then it may not accelerate. If one is on wheels, then it might accelerate. If the masses are different, then the A's might be different. Okay, but the actual collision involves one force here and then the same force here. This one feels one force, this one feels one force. Okay, so it's got to be two separate objects feeling two different forces. Those forces are the result of Newton's third law, and they will be equal and opposite. So I want to use Newton's third law to explain why the total momentum of a system must be conserved during a collision. Okay, how can I do this? Well, let's start in the beginning. During a collision, what happens? So during a collision, one object applies a force. Where? On the second object. Okay, so this is where we start. One object applies a force onto the second object. What does this create? This creates an impulse. Which increases the momentum of our second object. But Newton's third law, we want to use Newton's third law, right? So Newton's third law says that object 2 applies an equal and opposite force back onto object 1. See, here's where we've got this third law reaction force. We have one force coming from object 1 onto object 2. The reaction force is object 2 then returns an equal force back to object 1. So if it does this, this is actually going to create an equal, an opposite impulse. Now the initial impulse increased the momentum of object 2. This is backwards, so that's actually going to decrease the momentum of object 1. But these are the same size forces. These are the same impulses, just opposite directions. So however much the momentum was increased of the 1, that was due to the impulse. That same impulse is aimed the other way and is going to be decreasing object 2's momentum. So it's going to create an equal and opposite impulse, which will decrease the momentum of object 2 by the same amount. So how does this answer the question? Why does this tell us that total momentum will be conserved? Well, I've got two objects. Maybe one has some momentum, maybe the other one has some momentum, whatever their starting positions are. When they collide, one is going to add momentum to this, and the third law reaction force is going to create an equal and opposite impulse, which is going to decrease the momentum of this by the same amount. So however much this one goes up, that momentum has to go down on this one. So overall, we still have the same total momentum. Now, there's really nothing that we can do to prevent this from happening. It doesn't matter what type of collision this is. There's nothing we can do to prevent this from happening. You're going to get equal and opposite forces. What I've got right here, two force sensors. Okay, if I push on one, you can see the red numbers start to change. If I push on the other one, you can see the blue numbers start to change. So what I'm going to do is I'm just going to take these two force sensors, I'm going to push them into each other. All right, it's going to represent a collision. So here we go, let's collect some data. I'll hold this one still, this one bumps into it. Whoa. Hold this one still, this one bumps into it. Whoa. If you notice, the red graph and the blue graph are showing the exact same force distribution over time, just one's positive, one's negative. If I were to take the area underneath this right here, that area represents the impulse. That was a 1 Newton second impulse. Well, the area under this one is negative 1 Newton second. So that means that the momentum of one increased, the other one decreased by the same exact amount. Well, what if they're both moving? I just held one still and the other one moved. All right, fine, I'll move them both. Move them both slowly, quickly. Whatever combination I do, I'm going to get a mirror image as these two things collide. So these two carts, whenever they hit, whether one is stationary, the other one's stationary, whether they're both moving, whatever it is, when they collide, we're going to get equal and opposite forces spread out over the same time intervals, no matter how I do this. And that's going to result in equal impulses on each object, one in one direction, one in the opposite direction. So one's going to increase its momentum, the other one's going to decrease its momentum by the same exact amount. Okay. So I'm going to switch back over here. So how can we write this as a statement of conservation? When you're trying to explain your answers, it's important to phrase things appropriately to kind of pick a good starting point. Some people have been asking me on Twitter, well, how do I know what to describe, what to explain? How far back do I go? Well, starting with a statement of conservation is a great starting point. My change in momentum for my system, I can even notate this, is going to be 0. Okay, so that means that my initial momentum of my system will equal my final momentum. Well, the initial momentum of my system will be the mass and velocity of my first object plus the mass and velocity of my second object. One of those might start out at 0. They both might start out at 0, or they both could have some value. Could be positive values, could be negative values, whatever it is, it is. Now afterwards, it's going to be the momentum after the collision of my first object and the momentum after the collision of my second object. Now, sometimes they stick together. So you might see this, you might see a derivation with M1 and M2 added together and then just a single V prime. Okay. Now we could spend all day calculating conservation of momentum problems, plugging in M, plugging in V, figuring out what's 0, assigning the positives and negatives, crunching numbers all day. Okay. I'm not here to give you practice with that. You've probably had a lot of practice with that. You can easily practice that with lots and lots of examples. What I want to look at today is actually going to be more focused on predictions and explanations. Okay, so I want you to look at this problem. I've got two bullets, equal mass, and they're shot at equal speeds. So if bullets have equal mass and equal speeds, that means they have the same momentum. They're launched at identical stationary blocks of wood. Okay, so there's two blocks of wood. Each of those blocks has the same mass and a velocity of 0. One bullet's made of rubber, so it bounces backwards off the wood. The other bullet is made of brass and it passes through the block of wood. In both cases, the block of wood will start to move. Which block moves faster after the collision? The one hit with the rubber bullet, the one hit with the brass bullet, or neither? They both will have the same speed after the collision. Now, you could probably take a guess. You might guess correctly, you might guess incorrectly. But what's going on inside your brain right now? What's your thought process? I'm willing to bet most of you are trying to picture that last equation, that M1 V1 plus M2 V2. Okay, V2 is 0. The second block starts out at 0. That equals M1 V1 prime plus M2 V2 prime. Okay, well, what's the velocity of the bullet afterwards? What's the velocity of the block afterwards? Oh gosh, I don't have the mass. I don't have the velocities. How in the world am I going to solve this? Well, if you try and solve this mathematically, it's going to be challenging. You could make up some numbers. That's fine, as long as you're really careful, as long as you recognize that, hey, the rubber bullet, when it bounces back, has a different velocity vector, things like that. But this problem is a little bit tricky to solve using that sort of safety net of your calculations. So what I want to do is I want to look at some very simple collisions, some things that you can easily predict and some things that you've seen and probably calculated dozens of times. But I want to try and explain them in a different way. And instead of looking at individual M's and V's throughout, what I want to do is I want to take this equation. This is my conservation of momentum. And I want to just compare this term to this term. So from here, M1 is going to experience a change in velocity going from here to here. That might be an increase, it might be a decrease, okay, but it'll experience a change in velocity. M2 will experience a change in velocity. It might be an increase or a decrease. It's going to be the opposite of whatever the other one's change is. This represents how much momentum, or how much the momentum has changed for our first object. This represents how much the momentum has changed for my second object. Now, however much this momentum decreases by, this one will increase by the same amount. So I'll just put some absolute value symbols on here and we'll just compare the magnitudes, and we can say that these magnitudes will be the same. So what I want to do, rather than looking at specific M values and V values and grabbing my calculator every time, I want to see if I can answer or explain some simple collisions using this concept. How can I compare what's actually happening to that first cart? How does its momentum change? And then do we see that same change as an increase for the second cart? All right, so I'm going to switch over, see if this will work, see if I can find the right video. All right, hopefully you can see this. I've got two carts, equal masses. They've got a spring in between them, okay? This is going to be what we call a recoil problem or an explosion, where we start in the beginning, okay? So what's the total momentum of this system right now? 0, right? M1, V1 is 0, M2, V2 is 0. It's not moving. So at the end, we need to have the same exact momentum. Momentum is going to be conserved. We have to have no momentum. Now, if I let these things go, you can see that they move off. One goes to the left, one goes to the right. I'll play them again. Now, what do you notice about their speeds? Just visually looking at these, what do you notice about their speeds? Pretty similar, right? Well, that's because we know if we were to plug in the calculation, we'd have 0 on the left side, and on the right side, we'd have M and some positive V plus M and some negative V. In order to satisfy the equation, that positive V would have to be the same magnitude as that negative V, okay? But how can we explain this talking about the change in momentum for each individual object? Well, let's look at just the card on the left. Just the card on the left, how much momentum does it have right now? None. Now, when it starts to move, it's going to have some momentum to the left. Let's call that negative momentum. In this particular example, we'll call that negative momentum. So that means it experienced a decrease of a certain amount. Its momentum went down by a certain amount. Well, that means the other one had to go up by a certain amount. So that means that its momentum had to increase. So let's see if I can switch back over. So whatever the change in momentum was of our first one, this is going to be a decrease. It now has a negative MV. The other one's going to have to experience the same change in momentum, but as an increase. So now this will be positive MV. Equal mass on both sides. So we're going to get equal magnitude velocities or equal speeds on both sides. Okay. All right, let's go to another example. Let's take the same setup, except for now I have unequal masses. It might be a little hard to see. I'm sorry. The one on the right has a couple extra blocks on there, those little black masses on the top. So the one on the right actually is going to have more momentum, or excuse me, more mass. So when I let these things go, I want you to predict what is this going to look like in terms of how fast are these going to move away from each other. All right, here we go. One more time. Now you can see the one on the left is moving much, much quicker. Okay. Now, if you plugged in all these values, you could calculate, all right, we've got M1, V1 equals 0, M2, V2 equals 0. So, and then on the right side, I'm going to have a positive momentum and negative momentum. Okay, that's great. Let's go back to a little whiteboard here. What we're trying to do is we're trying to compare the change in momentum of our first one to the change in momentum of our second one. Well, this one, decrease in momentum because now it has a negative MV. This one has to experience the same change, but as an increase. So it's going to be positive MV. Except for here, this MV is actually 3M to this 1M. So that means this is going to have to be 3V to this 1V. Okay. Again, however much momentum goes down for one object has to go up for the other. Now, this is a little bit abstract because decreasing of momentum here looks like 0 down to a negative number. So let's switch over to a different example. I'm going to switch over to, let's see, which video am I looking for? Here we go. Here I have an elastic collision. An elastic collision, I've got little magnets in between these. So when they collide, you can see this. Almost looks fake, right? It comes in, they hit with these little magnets, so it transfers all of its kinetic energy. It's very, very close to an elastic collision. Now we know that if I were to set up my equation, m1v1 plus m2v2, all right, great. You've got the mv over here plus 0 will equal 0 plus mv over there. Same m, same v's. Great. So you can do it mathematically, but let's talk about it conceptually. Let's look at just the cart coming from the right. It has momentum right now. Now it has none. Was that a change in momentum? Yeah, absolutely. See, the cart on the right had a decrease in momentum. It had momentum, now it went down to 0. Well, the cart on the left has to experience the same increase in momentum. It went from 0 up to the same amount. Now, because they both have the same masses, however much this velocity went down, that velocity is going to have to increase by the same amount. Now, what if we switch these? Let's switch to a elastic collision with unequal masses. Here it comes. Now the calculation here gets a little more interesting because you have velocity values for both afterwards. But now I want you to watch this again, but only watch the cart on the right. Just watch the cart on the right. Does it slow down? Yeah. Does it slow down a lot? No, but it does slow down a little bit. So what does that look like in our analysis? Well, the cart on the right is going to lose a little bit of momentum. It slowed down. It had a pretty small delta V. The cart on the left has to experience the same increase in momentum, but it's moving pretty quickly. That's a very large delta V. How is that possible? Well, because this has a larger mass and this has a smaller mass. The masses are unequal now. So however much momentum was lost by the first one is now gained by the other one. But that loss in momentum doesn't look like much visually. That loss in momentum doesn't look like much. Where'd it go? It doesn't look like much for that first cart. If you watch it, you're like, I think it slows down a little bit. It doesn't look like much because most of its change in momentum is going to be, it's got a little delta V, but it's got a big mass. Now it looks like a huge change for the cart on the left. Oh my gosh, it's cruising now. Well, yes, but that's because in order for it to show the same increase in momentum, because it has a smaller mass, it has to have a much larger change in velocity. Okay. So what does this have to do with our practice problem? Let's go back to it. Let's analyze this, but just looking at the momentum of the bullet. I want to start with the brass bullet. It has M1, V1. It says it's going to go through this block. So it still has a mass and it still has a velocity. Is this going to be a little bit slower than before? Yes, absolutely. So is that a change in momentum? Yes, absolutely. So this brass bullet will have a small change in momentum. It slowed down a little bit as it goes through this block. What about the rubber bullet? It has the same MV to start with, okay? But afterwards, does it go through? No, it bounces back. Whoa, so that's actually a negative V. So picture our velocity. Positive numbers, here's 0, here's our negative numbers. The first one had a velocity here and then it slowed down a little bit. That's the delta V. This rubber bullet started here and it bounced, it reached a speed of 0 and then bounced back the other way. So that's the negative V. So that means this rubber bullet experiences a very large change in momentum. Well, remember, momentum is conserved because however much the momentum decreases for the one, it'll increase for the other object. So with the rubber bullet, the momentum of the rubber bullet decreases a ton. So that means the block has to account for a massive increase in momentum. With the brass bullet, it goes through, it slows down a little bit, so it's just a small decrease in momentum, so the block only gets a little increase in momentum. So which one's going to move faster? The one that's hit with the rubber bullet. Why? Because it'll experience a larger increase in momentum. Why? Because the rubber bullet experienced a larger decrease in momentum. Okay, so remember, within a system, any momentum that one object loses, the other one has to account for the increase. So if you have two clearly defined objects, a bullet and a block, et cetera, something like that, two carts, things like that, it's really easy to define M1 and M2 and their individual velocities. So it might be a logical approach to try and use our earlier equation, either conceptually or mathematically. But what if two objects are just individual parts of the same larger object? Like yesterday's practice problem. Yesterday's practice problem had a person walking on a raft. Okay, so what if the two objects are part of the same larger object? It's not so easy to identify the individual parts as they move around, right? They're kind of attached and they're just redistributing. So how does that affect the motion of this? Well, objects have a center of mass. All objects have a center of mass. Okay, we typically treat objects as a single point. In a system, each individual object has a center of mass, and then the system has an overall center of mass. Once we find the overall center of mass, then we can treat that whole system as if it's one object with a total mass at that singular point. What does that look like, and how in the world does this have anything to do with the problem? Well, again, our previous method, we find the sum of the individual parts. We find the momentum of one object and the momentum of the other one separately. In this scenario, it's kind of, the lines are sort of blurred. Everything's sort of attached together. So we want to calculate the momentum of the whole system at once, put all the mass at its center of mass. And we can do that by taking the total mass of the system. And instead of the velocities of the individual parts, we look at the center of mass and what is its velocity? Where is it moving? Now, in order to do this, we have to be able to identify it. And the scenarios you'll get, or that you might see in P1, are going to be fairly easy to identify where that center of mass is located. What's important to remember is that if all the forces acting on something are internal, then that means that the momentum of the system remains unchanged. We talked about this. If the forces are inside, then any force you apply, you're going to get a reaction force, Newton's third law reaction force, which is going to create the opposite impulse. So any momentum that's added to one thing has to be taken away from the other, so it's going to be conserved. So if the total mass stays the same, and we need the total momentum to stay the same, then that means that the velocity of our center of mass has to stay the same. So I'm going to write this as delta V center of mass equals 0. Is that the same thing as saying V center of mass always equals 0? No, it means that the change will be 0. So if it starts out at 0, then it'll stay at 0. If it's already moving, then it will continue moving. So let's take a look at this. Where's the center of mass of this system? Well, the person has a center of mass right here, and the block has a center of mass right there, or the raft. It says that they have equal masses, so they're both contributing equally. So where is their combined center of mass? Right there. What's the velocity? It says they're standing still, so the initial velocity of the center mass is 0. So what's the initial momentum of my system? Well, momentum of the system is mass of the system and the velocity of the center of mass. Well, if this is 0, then the momentum of the system is 0. Okay. Now, the interaction between the student and the raft will involve just internal or external forces. The person's feet up against that raft, these are all internal forces. So any forces between these are going to be internal. It's just between the raft and the person. That's how that person's going to walk forward. So that means that the total momentum will not change. All right, so what does this look like? Let's see if we can get our answer here. Student moves. Where would the center of mass be located? So if this student moves, now they're over here. So their center of mass is right there. The mass of the raft is right there. So that means that the new center of mass would be there. Remember, it was over here. Would that violate any conservation principles? Well, remember, the center of mass had a velocity of 0. Nothing was moving before. Yet now as this person walks, the center of mass is going to just kind of move over there. That doesn't sound like a velocity of 0 anymore. So does that violate any conservation principles? Yeah, it absolutely does. So what must happen to prevent that? Well, we need our center of mass to still be right there. The person has moved to the right, so what could the raft do to counteract that movement? Well, the raft could move back this way. See, what we need is we need to find a scenario where the center of mass is still in the same spot. So if I look at all these examples, where's the center of mass? Well, let's look at A. Person's mass is there. Raft's mass is there, so center of mass is there. Nope, that's not it. Part B, the person's mass is there. The raft center mass is there. So that's CM. Is that in the same spot? Nope, so that means it moved. So it violated our conservation of momentum. Here, the person's mass is there. The raft's mass is there. So the center mass is there. Ooh, that's right where it started. I think we might have our winner. Let's just confirm person's mass there, raft there, center there. Nope, not that. So our answer is going to be this. Now, how would this look different if the mass of the student was much bigger than the raft? Well, if the mass of the student was much bigger, you'd have these two center of masses here, but the student's mass is carrying a lot more weight, so it's going to keep the center mass really far over here. If they move, well, now the center mass is basically going to be over here. So if the mass of the student was much, much bigger, then as the student starts to move, the raft is going to have to move a whole bunch to make up for it. So we're going to be more like letter D. How would this look different if the mass of the raft was much larger? Well, if the mass of the raft was much larger, we'd have the person's mass, okay, great, and the mass of the raft. So it's going to keep the center mass really close to the center. So as the person moves over to here, the center mass is still basically right at the center, maybe move just a tad. So we only need the raft to just move just a little bit over, just to kind of keep this thing balanced out. So we're going to look more like this, more like example B. Example B is like walking along the deck of a cruise ship, right? Yeah, you moving to the front technically moves the center of mass of that system, but ever so slightly, probably not even a measurable amount. This top example right here is like you trying to run on a skateboard. You take one little step on a skateboard and that skateboard goes flying behind you. Why? Because you start shifting your mass and the skateboard says, wow, I've got to counteract that change. I've got to keep our total center mass in the same spot. So I better move a whole bunch, and it moves way further than your little step was, and off it goes. Now, does this apply to collisions? It actually does. I actually want to go back to our videos here. We'll pick whichever one we want here. Let's see. Whoops. Let's start with our explosion here, our recoil problem. Where's the center of mass? This one has a mass. Oop, can I draw on this? Oh, I don't know if I can draw and advance. Sorry, guys. This one has a center mass right there. This one has a center mass right there. The combined center mass is right there. Now, as I play this video, go frame by frame. Move it a little bit. Well, now this one has a mass over here. This one has a mass over here, but the center of mass is still dead center. Let's try a different one. Here we've got our explosion with unequal masses. Okay, so can I notate? Mass here. Whoops, not let me do this. Mass here, but this one's a little bit bigger. So I'm actually, instead of putting it in the center, I'm going to put it over here. This is going to be the center mass of our system. It's a little bit larger mass, so it pulls it over a little bit. Okay. Now let's let this play. Too far. Back it up. All right, and let's see what this looks like. Center mass of this one's here. Center mass of this one's way over here. So does that mean that the combined center mass is here? No, because remember, this one has a way bigger mass, so it's going to pull it. We've got this, we've got this. This would be the mathematical center, but this one has a larger mass, so it keeps it, and the actual center mass is still here, exactly where we would have expected it to be. How about during let's find one of our elastic collisions. Here we have a scenario where the center of mass is not stationary. So how does this work? Well, it's gonna be a little tricky because I can't write and advance. So let me do this. I'm gonna go ahead and I'm gonna stop this right where they collide. Okay, this is where our collision starts. So that means that our center of mass right now is right here. These are equal mass carts, center of mass. It's gonna be dead center between them. Now I'm going to back this video up. I'm just gonna back it up 10 frames. I lost count, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, where's the center of mass now? Well, it's right here. That's one cart, other cart, it's gonna be equally between those. So this was the center mass and then it moved to there. So in this case, the center mass does not have a velocity of 0, but whatever its speed is, it will continue to move at the same speed. So let me go ahead and go back to our point of collision. And then we advance 10 frames afterwards. 6, 7, 8, 9, 10. And we'll go back to our notation. And if you look, here's 1m, there's the other one, and directly in between them, we've got our center of mass. So you can see that the center of mass has moved from there to there. And if I continued moving this, then the actual center of mass of the system would continue to move. So let's kind of summarize here. If I have an internal force, it's a force that's coming between these two objects within the system. It might apply an impulse that can change the momentum of one part of the system. But keep in mind, Newton's third law is going to create an equal and opposite force, so that'll create an equal and opposite impulse. So any increase in momentum that the one experiences will come at the immediate expense or the decrease in momentum of the other one. Now, internal forces cannot change the overall momentum of the system, so that momentum is going to be conserved because as one increases, the other one has to decrease by the same amount. Now, that might look different. The velocity change might be different. Delta V might be different than delta V because the masses might be unequal, but that product of MV will change by the same amount as the product of MV will change for the other one. Now, this entire system can be treated as a single object with the entire mass at the center of mass. Now, the videos I was showing you, it would be probably trickier to explain one of those problems using this center of mass concept. I just wanted to show you, just as a proof of concept, that it still applies. Typically, I would recommend if you're dealing with multiple objects moving, whether it be carts or blocks or things like that, then stick with the more traditional M1V1 type approach. Or if you have numbers, that's great. Or look at how much the momentum of one cart decreases and recognize that the other cart must display the same increase in momentum, because the total momentum has to be conserved. Where I would use this last piece, treating the whole system as a center of mass, is if you have, again, a scenario like that student walking on the raft, where you have these two objects and they're not necessarily colliding and bouncing and moving somewhere else, but you're just redistributing mass within that system, okay? So you move part of you one way, and so it kind of scooches part of the system the other way, things like this. All right, so if you have a scenario where you've got individual parts of your system kind of being rearranged, then you need to be able to track that center of mass and recognize, okay, well, the other part of the system has to move to keep that center of mass where it was. This is an example problem that can be addressed kind of in all these different things we talked about. You've got a student sitting in a fixed position on a boat. So picture you've got a boat and they're like buckled into a seat or something. So wherever they go, the boat goes, they go together. They're holding on to a ball, object with a mass. They throw it to the right with a speed v. While it's in flight, the boat moves to the left, but at a speed much slower than the object. We can assume that the student and boat together have a much larger mass than the object, and then we can assume any resistive forces between the boat and the water are negligible. I want to see if you can explain why this boat moves with a slower speed than the ball that was thrown, but I want to see if you can do it three ways. Can you explain why using Newton's laws and forces? Can you explain the difference using conservation of momentum for multi-object systems? And can you explain the difference using this final method, analyzing the system center of mass? Go ahead and take a screenshot of that. I'll go ahead and kick off tomorrow with this. Feel free to ask questions about anything from the lesson on Twitter. I will be here. Glad to help. Hope this was informative. Again, don't hesitate to reach out with questions. And I hope you guys enjoy the rest of your day.